Are you able to hear me?
Yes, sir.
Yes, sir.
Okay. So this was the last slide which I shared yesterday, where we talked about that how do you locate different planes if the Miller indices of the planes are given, and then how do you decide whether they are crystallographically equivalent or they are not equivalent. So I hope you have gone through this. Meanwhile, I have been posting today the recorded lectures by compressing them, and I have been able to locate, I think, 4 or 5 recordings which I have shared with you since morning. I hope you have received that in the classroom.
Yes,
Is that
sir.
right? Okay.
Yes, sir.
Okay. So I still have only 50 students in my class. Anyway, so we move ahead and let us see that what other things we can talk about as far as Miller indices are concerned, and then how do you solve some basic problems. So the ones which I talked yesterday were basically a few problems from the textbooks which we are trying to solve. Similarly, now come to this particular problem. So for this one, what is given to you is the on the left hand side. So the data provided is here. So what does the data tell us? The data tells me that the directions the directions of a unit cell have been represented here in terms of the Miller indices of direction. So the first one here happens to be the 1, 0, 0 direction as well as the 0, 1, 0 direction. And similarly, accordingly, this is 0, 0, 1. Then I have the next one is 0, 1, 1 as well as 1, 0, 1. And the last one is 1, 1, 0. Okay. So this is the data provided, and what I'm supposed to find, we are supposed to find here the crystal structure. You are supposed to create a unit cell before doing that. So we will try to create the unit cell here using these dimensions which are provided to us. The problem is clear?
Yes, sir.
Aditya Prakash, Padi.
Hello? Yes, sir.
Okay. So the problem is clear that what we want to do, we want to create a unit cell and then identify which crystal structure this is representing. The directions are, the dimensions in these directions are shown to us. So the black dots here are nothing but the reduced atom model. We call it as a reduced atom model. Means although the atoms are shown very small, but they are actually just for clarity that we are showing it like this. Is it right? And we are supposed to create the unit cell. So what shall I know? The directions are given, and I shall be able to locate these directions in our unit cell here. This is what is precisely required. So can we start this problem? Aditya Prakash, keep your mic on.
Yes, sir.
Okay. So the first one happens to be your 1, 0, 0 direction. 1, 0, 0. So I want to locate this 1, 0, 0 direction. 1, 0, 0 direction in this. I've just created a unit cell here for ease, and I want to locate that where is the 1, 0, 0 direction. So
Sir,
can
the
you?
origin. Sir, where is the origin?
Origin actually, okay. Let's see. The origin is here.
Yes, sir. Sir, then the outermost.
Then this happens to be your
Yes, sir. 100.
100 direction. Is that right?
Yes, sir.
If I choose the origin here, so this is slightly moved out, but anyway, you can take it like this. So if I take the origin here, on the next corner, it is showing you. You are able to see the annotation.
So I can't see the next origin, sir.
Yes, it is. There is a delay. Now
Yes,
it
sir.
is
It's visible. Yeah.
okay. So if I take the origin here,
Sir,
then
the
what will be the
direction
one?
is same. Direction
Yes.
is same, but
Then this will be your 100 direction.
yeah, sir.
Okay. If I choose the origin here, let it come. If I choose the origin here, there is a delay here. Let us see. I am also observing the delay on my screen. The second monitor is showing a delay. Yes. Now it is
Yes,
clear.
sir.
If I choose
Yeah,
the
sir.
origin here, now the
So
direction
the
happens to be the same, but only thing is the direction vector is now just like this. Is that right?
yes, sir. It's at minus sign, sir. So it should be outwards.
Okay. If I say minus 100 and 100, are they same?
Sir, minus 100 and 100 are
100, are they
opposite in
equivalent?
direction.
Are they? No, no, no. That's right. You're right there. My question is, are they crystallographically equivalent?
Yes, sir.
Yes, that's what we shall know. Okay. So if I have located this 100 here or 100 here, I know that this edge length of the unit cell happens to be how much?
A or 1.
No, it is from this example that you are taking up. So you are
Okay,
taking
0.40 nanometer.
0.40 nanometer. So this edge length happens to be 0.40 nanometer. Is that right?
Yes, sir.
Okay. The second direction which is given, so I have located 100. The second one is 010. 010. So where is 010? If I go by my original one, so I take the origin here only,
It's along
where
the
we started from.
y-axis.
So then if I take the origin on my original one, I say then this direction happens to be your 010 direction. It is coming up. I hope you can get, it's the y-axis actually.
Yes, sir.
It is visible or no? No. Still it is.
Not yet, sir.
No, sir.
I know that. Now it is
So it's
visible.
visible now.
Now it is visible. It is 010. अच्छा है थोड़ा धीरे धीरे बोलना पड़ता है ना समझ भी आना चाहिए ना they understand man can say human so that is why they are providing a delay here so you have 010 and this provides me the second edge length so this lattice constant also happens to be 0.40 nanometers. Is that right?
Yes, sir.
Okay. So now comes the third direction 001.
Sir, it's along z-axis.
It's long z axis, so you're right. So if I take it this way, this is along the z axis. Let it come up, which gives me now it is there, which gives me that the dimensions of this unit cell along the z axis are 0.50 nanometers. So this unit cell is having first thing I know is A. If I take this as A, if I take this as B, if I take this as C, it tells me that A equal to B not equal to C.
Yes, sir.
Is it right? So
Yeah.
it is not a cubic system. It is what
Tetragonal, we can guess if angles
you
are
can
90
guess.
degrees.
You can start. Yes, the angles are 90 degrees. We will try to conclude that also. So let's go further. So right now I get that okay, it is not a cubical system. That is what is clear to us because the z lattice constant is not equal to x and y direction. A and B are equal, but C is unequal. Okay. Let's come to the third, this one. So we have now directions given here as 0, 1, 1 and 1, 0, 1.
Yes, sir.
0, 1, 1 and 1, 0, 1. So where are these?
0, 1, 1 is the diagonal to the
Yes.
back side of the plane.
0, 1, 1 can be located here as the diagonal there, or it can be the, even if I choose the origin here, I can say it is the front face diagonal also. Anyway, they are equivalent. So if I take even, I will, for ease of marking, I will say that this is what is there, and this happens to be your 0, 1, 1. And where is 1, 1, 0? I'll come to
Leftmost
this.
plane,
No,
diagonal
so
of
come
left.
to 1, 1, 0.
1, 1, 0.
1, 1, 0, the last one, this one.
So it's the diagonal to the bottom plane.
Yes, bottom or the top plane. I can
Yeah.
say that, and keep it in mind that what you are showing. So I am now locating this direction also, which we say that this direction then happens to be 1, 1, 0 direction. And you find that there are 3 atoms here. So there is 1 atom located here also at the bottom face. There is one here and here. Similarly, on this face diagonal that you have marked as 0, 1, 1, there is also another atom shown here. Can you see?
Yes, sir.
Similarly, will be the case for the top face. So there will be one atom here. So with this information, we already concluded that this unit cell does not belong to cubic. This seems to belong to a tetragonal system. But in the tetragonal system, I can have primitive tetragonal, tetragonal I, that is body centered tetragonal, tetragonal F, that is face centered tetragonal, and tetragonal C, that is only end centered tetragonal. Is it right?
Yes, sir.
So which one it seems to be like now? PIFC, which one it is?
Face center.
Yes, it is face centered, because I find that along this 0, 1, 1 direction also there is one atom located here. And along the 1, 1, 0 direction also, that is on this bottom face also, there is an atom at the center of the diagonal. On the front face also, you have an atom at the diagonal of the face. And if you see 1, 0, 1, 1, 0, 1, 1, 0, 1, it can be here, this face.
Yes, sir.
And there is an atom here also. So if this happens to be your 1, 0, 1 direction. So this concludes that this happens to be a face-centered crystal system. Is that right?
Yes, sir.
This happens to be a face-centered one, where we find now that now the dimensions are also given. As I said, it is 0.4, 0.4, 0.5, and 110, the body diagonal happens to be 0.566 nanometers, and the face diagonal happens to be 0.64 nanometers. From these dimensions and the dimensions of the edge lengths, which are 0.4 and 0.4 here, can we conclude about the angles?
Yes, sir.
What?
So using Pythagoras theorem,
Yes, yes.
if we
You can
obtain
find out that the angles are
0.566.
also 90 degrees. So this happens to be an orthogonal, a tetragonal system, which is a tetragonal F system, tetragonal face centered. Am I right?
Yes, sir.
So this is how you identify the crystal structure based upon the dimensions of the unit cell. And these type of examples actually tell us that how do you recognize the directions also. So they help us in visualizing that what is the meaning of these directions. I'll take a similar example. Let's see here. So you can switch off your microphone, please. I'll pick up somebody else. Manish Kumar.
Yes, sir.
Okay. So I have a similar problem. Now the data is given here. What you observe. This is the data. In the
Yes, sir.
previous case, the directions were shown, but in this case, what we are showing, the planes. The planes are shown. So I have the 0, 0, 1 plane shown here, 1,
Yes, sir.
1, 0 plane shown here, and 1, 0, 1 plane shown here. Is that right? The
Yes, sir.
question remains to be same, that I want to identify that what is this crystal system and what is this particular crystal structure. When I say crystal system, I may be interested about cubic, orthorhombic, tetragonal. When I say structure, I add into this whether it is P, F, I, C. So this data of cubic plus tetragonal, there are 7 crystal systems, tetragonal, orthorhombic, combined together with this information of PFIC will give me crystal structure. ये ठीक है?
Yes, sir.
Okay, so can you help me now in finding out this? I have the first data 0, 0, 1 plane. I have just already shown you that these are the 3 unit cells in which we will draw these planes. So where is the 0, 0, 1 plane in this first picture? This is the first one at the top. 0, 0, 1.
Yes, sir. X axis के पैरेलल और Y axis के पैरेलल.
Intercept 1.
Intercept 1 आएगा Z axis.
1 आएगा. So if you take the origin at the bottom portion here, with this last corner here, the units, the 0, 0, 1 plane will be which plane?
Sir.
The top plane, this plane.
Yes, sir. Yes, sir.
Because you'll have, now this will be what you refer to as your 0, 0, 1 plane. And the dimensions of this are shown to you. Can you see that?
Yes, sir.
It is shown
0.30 nanometer.
Yes, 0.30 and 0.40. So you can mark any of them here. Let's say I mark this as 0.4 nanometers, and this side I marked as 0.3 nanometers. Okay?
Yes, sir.
Okay, let us mark the second plane now in the second picture. So 1, 1, 0 plane.
Sir, along the diagonal.
Yes, 1 intercept on the x, 1 intercept on the y, plus 1 plus y, and
parallel to the Z axis.
Parallel to the Z axis. So I say this will be this plane.
Yes, sir.
The plane. And it has a atom at the center of this plane. So this has a atom at the center of this plane here. And the dimensions of this plane are also shown to you. The dimensions of this plane are 2.35 and 0.50 nanometers.
Yes, sir.
0.35 and 0.50 nanometers. Now, can you tell me which side is 0.50 and which side is 0.35?
Sir, a smaller one.
स्मॉलर वन तो ऐसे ही है भाई, वो तो मैंने दिखाया तुमको. कैलकुलेट, दिमाग चलाओ कोई अपना. ये टॉप फेस का डायमेंशन आपने निकाल लिया था ना. टॉप फेस इज 0.4 by 0.3.
Yes, sir.
So what is this diagonal then?
0.5.
0.5. पाइथागोरस थ्योरम याद कर लो थोड़ा सा. 0.4, 0.3. Anyone can tell me?
0.5. सर डायगोनल 0.5 आएगा.
0.5 ही आएगा ना सर डायगोनल.
Okay. Then what is the other side?
Other side is 0.35.
Other side is 0.35. So I say that this is your 0.5 nanometers, and this side happens to be 0.35.
Yes, sir.
Okay. So with this information, can you tell me, is it cubic, Unit cell?
No, no, sir.
It is not, because this side is 0.35.
Yes.
तो क्यूबिक तो नहीं है, फिर टेट्रागोनल है?
सर टेट्रागोनल भी नहीं है.
Tetragonal भी नहीं है, because A is also not equal to B. So I have a condition where A not equal to B, not equal to C.
सर
So
ऑर्थोरोम्बिक उसमें भी हो सकता है.
orthorhombic can be there if the angles are 90 degrees, because then it is
Yes, sir.
orthorhombic. But it is not a cubic one, and it is not a tetragonal one.
Tetragonal. Yes, sir.
Okay, let's mark the third plane. 1, 0, 1. Where is that? Let's show it on the picture 3. 1, 0, 1. Parallel to y-axis.
Parallel to y-axis.
One intercept on x.
One intercept on
One
z-axis.
intercept on z. Parallel to y-axis means this is the plane.
Yes, sir.
So this is your plane which we are referring to as your
101.
101 plane. And its dimensions are also shown to you. 0.40
Yes, sir. 0.40 upper side.
and 0.46. So this
Yes,
is
sir.
0.40 and the diagonal happens to be 0.46.
46.
So from this information, we shall be able to decide that this crystal structure happens to be an orthorhombic. What?
Yes, sir.
PFIC? Which one?
Sir, body.
Yes. Body centered.
Sir, I.
I लिखते हैं I. I is actually
Yes, sir.
written as body centered. So this crystal structure then happens to be orthorhombic I or body centered orthorhombic.
Yes, sir. Body center orthorhombic.
Okay. Switch off your microphone, please. So this is how you conclude from the given data that what are the crystal system we are talking about. These are a kind of what we call as numerical problems, you can say, but I will not call them as numerical problems. I will call them as conceptual problems, which make us understand the basic concept of indices of directions and planes. Okay, so let's go to our next topic, which is again related to the concept of directions and planes only. We call it as a Weiss zone law or Weiss zone law. Some pronunciation can vary. We say what it is also referred to as the Weiss zone law. So what is its implication and application, that will come later. But the Weiss zone law simply says that if I have a plane which has the indices HKL and I have a direction which has the indices UVW, if I want to conclude whether this direction UVW lies on the plane HKL, the necessary condition happens to be that HU plus KV plus LW must be equal to 0. HU plus KV plus LW must be equal to 0. If this is correct, if this statement is correct, then we can conclude that the direction UVW is contained in the HKL plane. So this is regarding your plane and this is regarding your direction. So we are saying that, and we will solve it now with the help of an example, that what is the meaning of that. So this law tells me that if a direction, you want to know whether a direction UVW is contained on HKL plane, you can check it out simply by finding HU plus KV plus LW. If this happens to be 0, you can conclude safely that UVW is located on the is contained in the HKL plane. Okay. So this
Actually,
is what
sir.
Yes.
Sir, question can be asked from any type of crystal structure.
Obviously, that is why books are provided. Don't depend upon my lectures only, na? Because I cannot cover 800-page book in 40 hours.
Okay, okay, sir.
All the crystal structures are same. Same means similar. If you understand what is the meaning of that and what is the meaning of directions, you can plot anything, whether it is orthorhombic, cubic, whatever it is. You shall know what is the fundamental concept behind that. So we are saying that this is what we refer to as is the equation for the V-zone law, which tells me that if a direction is contained in a plane, then HU plus KV plus LW must be equal to 0. Okay, what is the graphical meaning of that? Let us say I have this black plane shown here. Muhammad Zishan. Muhammad Zishan.
Hello?
Yes. Can you see this black plane?
Yes, sir.
Which is this one? Can you index?
Yes, sir. It is
Which
one,
one it
one,
is?
and
Yes.
it is one, one, and one.
This is 1, 1, and 1 plane. Okay, it's already written, but just wanted you to identify. This is the 1, 1, 1 plane. And similarly, I have the second plane, which I will try to draw as 1, 1 bar 1.
Yes, sir.
Where it will be located?
The x intercept will be 1, y intercept will be 1, and z intercept
Yes.
will be
So
minus.
where it will be located? Can you tell me where it will be located? I shall take the z-axis downwards
Yes, sir.
because I am going to negative z,
Yes, sir.
and then the intercept is negative
Yes, sir.
minus 1, and that means actually I am creating another unit cell below it, and then this green plane happens to be the 1, 1 bar 1 plane.
Yes, sir.
1, 1 bar 1. Can I create the same plane here also? I hope I can. If somebody says that I want to create it in the same unit cell, I can then say that okay, you take this, and then this red one happens to be your 1, 1 bar 1 plane. ऐसे भी कर सकते हैं?
Yes, sir.
Because you are just representing the plane. This 1, 1 bar 1 plane will be parallel to this 1, 1 bar 1 plane.
Yes, sir. Parallel.
They are parallel. So the planes which are having the same indices, they are parallel to each other. Okay, let's see. Then I am interested to know that which is the common direction to them. Which is the direction common to the 1, 1, 1 and 1, 1 bar 1 plane? Graphically, can I see?
Yes, sir. We can.
You can see which one? This is the common direction. This direction happens to be the common direction.
Yes, sir.
Am I right?
Yes, sir. Right.
ठीक है? Okay. We will try to find the indices of this direction. You can see it on the unit cell also, and we will try to solve it using the V-zone law also. That what is this? So if I say this is the direction which is common to 1, 1, 1 and 1, 1 bar 1, the indices of this direction are 1 bar 1, 1, 0. So this direction happens to be your bar 1, 1, 0 direction. Bar 1, 1, 0 direction means I am taking the origin. If I am taking the origin here, we'll say that this is bar 1, 1 on plus, and then we say it is 0 intercept on this. So this direction happens to be the bar 1, 1, 0 direction. This is as far as I see it graphically. So now comes the second idea which I was floating earlier, that if I can create the unit cell and the planes, the two planes in the same unit cell, it will look like this. Is it right? And these two planes will then intersect at FG, if FG is a line which I create here. Nikhil Bhardwaj.
Yes, sir.
So we find here that now I am showing that both these planes 111 and 11 bar 1 plane are shown in the same unit cell. ये दिख रहा है आपको? ठीक है?
Yes, sir.
So earlier we concluded this AB, along this AB was the common direction. Last slide में ये हमने कहा कि along this AB is the common direction to these two planes. But right now I am saying that these two planes are intersecting and they are creating an intersection line FG.
Yes, sir.
So I want to know that, okay, whether FG and AB are same or they are not same, whether FG and AB are same or not same. Incidentally, F and G happens to be the located onto the face diagonals of the left face of this. This is the left face and this is the back face. So F and G are located on the left face and the back face of this unit cell. And I can say here that in this this triangle ABC, I say it is bisected here. So CF is equal to AF, FG is equal to GC, and which tells me that FG is parallel to AB, which means that FG and AB must have the same
Miller indices.
Same indices in the Miller notation, which I say same Miller indices for your direction, which we said was 1 bar 1 0. Okay, so let's do it using the V-zone log algebraically. So I have the two planes 1 1 1 and 1 1 bar 1. Common direction if it is UVW. For this first plane, the V-zone law tells me that because whatever direction, if it is UVW to be contained in 1 1 1 plane, what shall be true?
Sir, it should be equal to 0.
What shall be equal to 0?
Sir,
This
the
one. This
yes,
one.
sir.
HU plus KV plus LW shall be equal to 0. And in this expression, what is HKL? HKL are the Miller indices of the plane, which in our example are 1, 1 and 1.
Yes, sir.
So I can say that for the direction UVW to lie on 1 1 1 plane, U plus V plus W shall be equal to 0.
Yes, sir.
Similarly, the second expression shall also be valid. Can you tell me why?
Yes, sir. Because here HKL are
Because for
what?
the second plane 1 1 bar 1,
Yes, sir.
the HKL are 1 1 minus 1. And then I say the second expression shall also be valid.
Yes, sir.
So by V-zone law, I can say that U plus V plus W equal to 0 and U plus V minus W equal to 0. So there are two equations which I get, and I can use these expressions to find out the common direction between these two planes, 1 1 1 and 1 1 bar 1 plane. So when I add 1 and 2, I get U is equal to minus W. Going further, subtracting 1 and 2, I get 2W equal to 0. Substituting these values, I get the answer here, that the common direction happens to be bar 1 1 0. So I can look at it graphically. I can find it by V-zone law. Graphically, finding out may be very, very tough. It was very easy for a plane which was very simple to draw. But many planes are very tricky to draw, and it may be really impossible to find graphically which are the common directions. And that is why V-zone law helps me to find out this. Is it right?
Yes, sir.
Okay. Okay. Let us come to a very important concept now. Interplanar spacing. Okay, can anyone tell me the meaning of this word? Rishabh Verma. Rishabh, Rishabh. Rishabh Verma. Rishabh
Hello, sir.
Verma. Yes.
Sir.
Yes. Can you tell me the meaning of this word? Interplanar spacing. What do you understand by this word?
Interplanar spacing means the void space that is left between the two identical things.
Okay. I can say this can be talked as a distance between the planes.
Yes, sir.
But which planes?
So the planes
which are similar, which have the same index HKL. Which have the same index HKL. What is the interplanar spacing between? How do these planes are spaced from each other? In a simple understanding, I can say that if I talk about let us say a cubical unit cell, I can say here that we said the front face of the cube was given as your which plane? Front face was indexed normally by us as which plane? What are the indices of the front face?
100.
100. Am I right? Is it right?
Yes, sir.
Yes, sir.
Okay. What is the back face of this plane referred to as? What of this cube is indexed as? The back face.
The minus 100.
Okay, 1 bar 0 0. Okay, okay. काजल शर्मा. बाकी तो कोई लोग सो रहे हैं सारे. Let us ask somebody else. Vipul Khetan.
Yes, sir.
Okay, so it is clear 100 and 1 bar 00.
Yes, sir.
Are they same planes?
Yes, sir. They are parallel.
They are parallel. Are they same planes? Try to answer my question. I am not asking they are similar planes. I am asking are they same planes?
Yes, sir.
How?
Sir, let's when we assume origin behind this, मतलब अपन जब 100 के पीछे origin लेंगे तो फिर वो उसका मतलब same वो आएगा, मतलब मिरर इंडेक्सेस आएगा.
You are correct to some extent. I will try to answer it in a different way. We what we defined stay here with me. What we defined a crystal lattice as. We say it is a repetitive periodic arrangement of atoms, and we then defined a unit cell, the smallest cell which repeated will create the lattice. यही कहा था हमने?
Yes, sir.
So we said that this is the front face, and I say that this is indexed as 100. But if you now say that these unit cells, there are number of unit cells placed or they are stacked with each other to create the lattice, I can say that there is another unit cell available here.
Yes, sir.
At the back of this. And the back of this it was 1 bar 00 for this unit cell, whereas the same plane now is actually 100 for the second unit cell. So I have the two unit cells shown here, 1 and 2. So for first unit cell, I indexed it as 1 bar 00, whereas for the second unit cell, it is nothing but 100.
Yes, sir.
Is that right?
Yes, sir.
Similarly, there will be a cell here also. Yes?
Yes, sir.
And there will be a cell here also at the bottom. And this gives me the concept of equivalency, that they are all same. Because when I say the top face, so it is the top face for the blue unit cell, whereas this is the top face for this red unit cell.
Yes, sir.
So this is how we talk about that. Now you answer, what is the meaning of interplanar spacing? Distance between planes which have the index H, K and L. HKL. So then I am referring to, we said HKL planes will be parallel to each other. ये ठीक है?
Yes, sir.
So then I am saying that what is this interplanar spacing? If these two planes are having HKL planes, and then what is this D? What is this D? This is what I want to find out theoretically. And this has a very important bearing upon one of the basic bulk characterization techniques, which is the backbone of crystallography, which tells us how you can experimentally evaluate the crystal structure of any material, whether it is, if it is crystalline, whether it is steel or aluminium or any other alloy, you can try to find out the interatomic spacing. We have certain conventions. We already know that the cell of the atom, the radius of the atoms for various elements is almost constant. They are located in a particular crystal structure that is also known to us. And if I give you any item, any material with the help of a technique called as X-ray diffraction, you can actually tell me that what is the crystal structure of this material. And from that, we can try to conclude that whether it is, which material it is. I'll tell you how we do that. But before going there, let us talk about interplanar spacing. So this is clear. What is the meaning of interplanar spacing? The distance between two consecutive planes which are parallel to each other. Right?
Yes, sir. Yes, sir.
Okay. Okay. Let me introduce one more concept here. So I said this is 1 bar 0 0. This is 1 0 0. Where will be 2 0 0?
Sir, 200 sir, just मतलब इसके
I will draw it again. Yes, I will draw it again for you so that it is easier for us. So we said the front one happens to be 1 0 0 and the back one happens to be bar 1 0 0, which is nothing but 1 0 0 for the previous one. So where is the 2 0 0 plane?
सर पैरेलल टू 100 एंड इससे पहले वाली जो भी यूनिट सेल होगा उसके फ्रंट फेस
No.
नहीं सर आधा मतलब उसके बीच वाला
0 means the intercept is half. 200 means the intercept is half.
Yes sir, between them.
So 200 will be here.
Yes sir, between them.
Okay. So I'll come back to this later. Let's talk about the concept of interplanar spacing first. So I am interested to find out DHKL. Interplanar spacing is normally written by a standard notation D subscript HKL, which means that I am trying to find out the interplanar spacing between the successive HKL planes. What is the interplanar spacing between the successive HKL planes? That is what we are interested to find out when I write it as DHKL. This DHKL is related to the Bragg's law. If you search on Google, you will search for Bragg's law. Your assignments are pending with me. I will post maybe 2 or 3 simultaneously. So Bragg's law, if you search for Bragg's law, it will tell you the simple expression it says is 2d sine theta is equal to n times lambda. 2d sine theta is equal to n times lambda. We will talk about this. Lambda here is actually the wavelength of the X-rays. This D happens to be the DHKL. This D is nothing but DHKL. So we will try to see later, once we understand the concept of DHKL, that how does we use the Bragg's law to find out the interplanar spacing. Keep it in mind, interplanar spacing is constant for elements. So iron will have some interplanar spacing for HKL planes, maybe 111 planes or 100 planes. Similarly, aluminium will have some different spacing, because, can you answer me now, why aluminium and let us say iron Fe will have different interplanar spacing between 100 and 1 bar 00? Uttamji Singh.
Yes sir.
Yes, can you answer me?
Yes sir, atom size बकरा होगी.
Because the atom size will be different. So if I normally, let us say Fe is having a BCC system, but I say it is beyond the 910 degrees, so it is also an FCC system. Aluminum is also an FCC system. So I say that these atoms are located here like this. But because the atomic radius happens to be different for aluminum iron, the size of the unit cell will be different. So if you remember, for FCC system, we already found that the lattice constant for a cubic system was given as याद है कुछ? हाँ जी, उत्तम जी।
जैसा
कुछ याद है क्या था? A, that is constant in terms of atomic radius for FCC. अभी कल ही करा था हमने कुछ ऐसा। पीछे लेके चलो। Let me take you back. थोड़ा पढ़ाई शुरू करोगे तो काम चलेगा भाई, नहीं तो मुश्किल हो जाएगा थोड़ा सा। क्या करें? मैं तो चलता रहूंगा आगे, तुम रुक जाओगे। इधर है कुछ दिख रहा है अभी?
जैसा
क्या है?
सर
What is A?
प्लेनर टेस्ट।
नहीं, क्वेश्चन मैंने आपको पूछा था दैट फॉर दिस एनीवन कैन टेल मी। तुम छोड़ो, कोई और आते हैं और किसी को पूछते हैं। Shreyasi, yes, I hope.
Yes,
I
sir.
don't know. I may be pronouncing it wrong, but anyway. Okay, so can you tell me what is A in terms of R?
So your
That is,
voice is breaking.
what is the value of lattice constant A for FCC crystal structure in terms of atomic radius?
I can't hear you.
You can't hear me.
Hello.
Okay, anyone?
Yes, sir, you are audible.
Anyone else can answer it for me?
Yes, sir,
2
A
root 2
equals to
R.
2 root 2 R.
2 root 2 r.
Yes, A happens to be, I've already written here, A happens to be 2 root 2 times the atomic radius. So I'll come back to this discussion that we were having right now. We are saying here that A happens to be 2 under root 2 times R. Because R is different for iron and aluminium and different elements, that is why the A value will be different, the unit cell size will be different. And if the unit cell size is different, the interplanar spacing will be different, because if I only see about these 100 and 1 bar 00, it is nothing but A. ऐसा ही है? Yes or no?
Yes, sir.
Yes, sir.
Okay. So let's, I think it is okay for today. We will get to this derivation next time, that how do you find out DHKL for different systems, and we will actually, I'll give you the answer first. At the end, I will have this expression, the yellow one, if you find here, we will use, this is for cubic systems, that DHKL happens to be A, that is the lattice constant, which can be termed in terms of 2 root 2 R for FCC. This one is for whole of the cubic upon h square plus k square plus l square root of this. So I can find out HKL distance between the successive HKL planes in terms of A and in terms of R. So this is the expression we will try to derive here. Not a difficult one, at least for engineering graduates, engineering students, not graduates. Okay, so I hope you understood some of the concepts today.
Yes.
Okay, I can only try to do that. See, we can only try to make you understand.